Sorry. Apparently Zoom is down. It's all these years, hasn't happened, but I guess was today. Trying to get this done on Microsoft Teams. So anyway, we are already like almost 9.5 minutes over time. So at the end, I will record. If you have to leave at 2, you can leave at 2. And hopefully it'll capture the rest of the video properly. All right, let's see. Transcript. I don't want transcript. Share my notebook. All right, let's hope this works. Okay, so we had stopped here. We were talking about applications of diodes. So diodes, we can describe diodes by we can use several different models to describe diode performance. Broadly classified, we break them up into large signal and small signal. Large signal means, well, as the name suggests, large. It's large enough to turn on the diode. Okay, so it must be at least large to turn it on. So if it's a regular silicon diode, turn on voltage is about 0.6 or 0.7 volts. So anything larger than 0.6 or 0.7 volts, which is enough to forward bias the diode, would be termed as large signal. Small signal is when you apply a small AC signal, like what we did for lab 2, where you applied a small signal of 50 millivolts, 100 millivolts, or less than a volt. Actually, less than the turn on voltage. Whether it turns on or not, it doesn't matter because we're applying a large DC signal and then we apply an AC signal on top of the DC. Okay, so when we do that, we call that a small signal. And so for both kinds of signals, the diode responds a little bit differently. One of the biggest applications, or the most common application for a diode, is as a rectifier, where we connect it to an AC input signal and the output is DC. We will look at rectifier circuits next week in detail, but for now, just suffice that it's similar to the peak detector circuit that we did in lab 1. Okay, so it's like a half-wave rectifier. It conducts in one direction, does not conduct in the other direction. Okay, so that's a rectifier circuit. We can also create OR and AND gates using diodes, but those are not very desirable. I will go over some of the circuit models, but again, these are not desirable to perform actual logic circuits. And then of course we already looked at DC restorer, not DC restorer, voltage multiplier circuits, the peak detector, and the clamper circuit. So there are many other applications of diodes. We can use them for wave shaping, giving different kinds of input waveforms and change the output. Okay, so we'll look at rectifier circuits later on, and then we look at logic gates also later on. For now, let's look into the diode model. Sometimes also known as the Shockley equation. Okay, Shockley equation, named after William Shockley, one of the founders or one of the inventors of the solid state transistor device. So ID, diode current, is equal to IS to e raised to VD over NVT minus 1. Let's take it one by one. ID is the diode current, is right here. VD, right there, is the diode voltage. These are the operating points of the diode, right? If you apply a certain voltage to the diode, we can calculate the current, ID. If we know the diode current, we can calculate VD. Okay. IS is the saturation current, which is a design parameter, and it is provided, the value is provided by the manufacturer on the data sheet. So it's designed, and it's manufacturer provided on the data sheet. Okay. N is the emission coefficient, it represents the non-ideality factor of the diode. The diode itself is a nonlinear device. Typical values of N range from 1 to 2. So it's between 1 and 2, but typical values for pretty much all normal operation diodes is just 1. So if we do not know the value of N, we can safely assume 1 for most analyses. Okay, it wouldn't make too much of a difference. And then VT, thermal voltage, is given by this relationship, KT over Q, Einstein's relationship, where K is the Boltzmann's constant, T is the temperature in Kelvin, and Q is 1 unit charge. So at room temperature, in room temperature, we take 27 degrees C or 300 Kelvin. Comes out to be about 25.8 millivolts. At 300 Kelvin. Okay. Obviously, room temperature is not the same everywhere. The room temperature here is probably less than 25 degrees C. So actually far less. So if it's, let's say 72 or 73, 40, about 20 degrees C. Okay. 72 Fahrenheit would be approximately equal to 20 degrees C. So that would be a temperature of 293 Kelvin. So that would make a slight difference in the actual thermal voltage. All right, so typically what happens is this exponent is far larger than 1. So we can put that if you want like quick analysis and quick results, and we do not care about the actual precise values or precise numbers, then we can ignore that 1. Also, emission coefficient N is equal to 1. So the equation can break down to simply IS to VD over VT. That's it. Two quantities, IS and VT. Okay, IS and VT. This is something we use in the lab too. Okay, so that's the diode equation. And if you wish to find the diode voltage from the diode current, simply take the log on the other side. So you'd have ID over IS, natural log, and then times VT. Okay, so that's the diode equation. So that is the fundamental equation that governs the operation of any PN junction. Okay, so later on, we will look at BJTs where you have 2 PN junctions connected back to back. So even there, this equation holds true. Okay. Now, oftentimes we want to make a quick analysis of any circuit. So in order to do that, use a model known as the ideal diode model. Okay, ideal diode model. And the assumption in the ideal diode is that when the diode is forward bias, it turns on. It does not require a forward voltage. Since it's ideal, there is no gap, there is no built-in electric potential. Any positive voltage, meaning it could be 0.000001 volt, is enough to forward bias the diode. And then in reverse bias, it's completely off. So the diode characteristic breaks down to, this is forward bias, and this is a reverse bias. A real life diode has a curve like this. Ideal diode is simply a vertical line at the y-axis, or 0 of the x-axis. So in forward bias, current is infinite. In reverse bias, voltage is equal to 0. And actually not 0, negative voltage. Current is equal to 0. So what we do is we replace we replace the diode with an open circuit when it's reverse bias. That should be reverse. So these are forward bias, and this should be less than. A few typos in there. Okay, so hopefully, let's see. Let's just do this. Hey, now it started working. Well, too late. Okay, so as I was saying, when the diode voltage is less than 0, meaning it goes negative, diode is reverse bias. We say the diode is off, we replace it with an open circuit. There is no connection between the two ends of the diode. When it's forward bias, meaning when VD is greater than 0, even a slight voltage, a small voltage is enough to turn it on. It's forward bias, diode is replaced with a short circuit. Okay, hence a short circuit wire. And this model allows us to quickly analyze any diode circuit. So in the lab, where lab 1 and even in lab 2, when we use the diodes, if we wish to analyze, we could say that when the voltage goes positive, diode turns on, capacitor starts charging. When the voltage goes negative, diode is reverse bias, replaces open circuit, capacitor has no place to discharge. So it holds the value constant. Then when it gets to the peak detector, it charges to a level of the negative voltage, depending on the connection. When it charges, it's going to hold the voltage across it constant. When it's, again, forward bias, the diode is now a short circuit. Capacitor can discharge through the resistor. Okay, so that's a quick and easy analysis using the ideal diode model. And we can analyze any kind of diode circuits using these models. Okay, so all we do is we determine whether the diode is off or diode is on by examining the circuit, making an assumption, and then we replace it with a short circuit or an open circuit. Then there's the offset diode model, because the ideal diode does not take into account the forward voltage drop that is required. So the offset diode model is exactly the same as the ideal diode model. Then the reverse bias it's exactly the same. It's replaced with an open circuit. But in the forward bias, if we want to account for the forward voltage drop, we replace it with a short circuit and a 0.6 volts battery. Because the voltage across the diode will remain constant, right? It takes about 0.6 to 0.7 volts to turn on. So it's up to you as an engineer to decide which model you want to use. 0.6, 0.7. If you use the Schottky diodes or germanium diodes, it'd be 0.2 or 0.3. No matter what you choose, that voltage will be held at a near constant value across that diode. So again, this is not accounting for the nonlinearity or the linear resistance there. All we are saying is the voltage across the diode is going to be held constant. So we can model it. We can model it as a short circuit in series with a voltage source, because that voltage is going to be held constant. So it's supplying that voltage between those 2 points. And so the same diode that we had is replaced with a short circuit. So it'd be the ideal diode. So the ideal diode in series with a voltage source of 0.6 volts. The book uses 0.6, so I'm going to stick with 0.6. Okay, so that's known as the offset diode model. It is also known as the CVD model, constant voltage drop. A constant voltage drop model, CVD. So far, so good. Does it make sense? Any questions? Okay. Oh, CVD, by the way, is also a fabrication process used in chemical engineering. It stands for chemical vapor deposition. It's also the method by which lab-grown diamonds are grown in the lab. CVD, chemical vapor deposition. Anyway, ideal diode model. The analysis steps are: we assume a diode state. We look at the circuit, we observe, and we make assumptions. So observe, look at the circuit conditions, make an educated guess, and assume whether the diode is on or off. If it's on, you replace it with a short circuit. If it's off, you replace it with an open circuit. Now your circuit has changed. If your circuit has changed, then you analyze based on the short circuit or the open circuit. Okay. Now, when you analyze the circuit, you can use any circuit analysis techniques you want. And if you assume on, and it's a short circuit, that means current is flowing through in the positive direction. So if it's on, then VD must be equal to 0. And more importantly, ID must be greater than 0. If it's a short circuit, it provides a pathway for the current to flow through. So if you make an assumption that the diode is on, then the diode current ID must be positive, must be greater than 0. Okay, it must be greater than 0. If it's 0 or negative, that means your assumption is incorrect. Okay, so if ID is less than 0, then assumption is incorrect. Make sense? Okay. If you assume that the diode is off, that follows that the voltage across the diode is either 0 or negative. Okay, so you need to check whether the diode voltage is less than equal to 0. Actually, it won't be 0. It'll just be less than 0 because it's the ideal diode. So if it's less than 0, negative, then the diode is off. Your assumption is correct. ID must be equal to 0. If it's an open circuit, current cannot flow through. Current's not flowing through, value is 0. So the important out of those two are these. When it's on, ID must be greater than 0. When it's off, VD must be less than 0. If VD is greater than 0, then assumption is incorrect. Okay, assumption is incorrect. If you make an incorrect assumption, there's only one other state possible, meaning if you assumed on first and you conclude that it's incorrect, the other state is off. So you just test it out with that other state and then prove your hypothesis or prove your assumption to be correct. Okay. So one diode, two states. If you have more than one diode, multiplies exponentially. If you have n number of diodes in a circuit, the possible combinations of the total states equal to 2 raised to n. Example, if you have two diodes, D1 and D2, either both are on or both are off. That's two possible states. Then it could be D1 on, D2 off. That's a third state. And then D1 off, D2 on, fourth state. So there are four possible combinations that you need to test. So again, if your first assumption proves incorrect, you have to try another one. If that one proves incorrect, try the third one. If that one's incorrect, try the fourth one. Okay. One key thing to remember is that if one state is incorrect, meaning let's say you assume, let's say, for example, you have n is equal to two diodes, D1 and D2. So possible states, 4, 2 raised to n. Let's say you start first with D1 on and D2 off. And it turns out that at the end of your analysis, D1 on is correct and D2 off is incorrect. So then you have to test for another possible state. Which possible state would you choose? D2 on, right? But it is not necessary that the answer D1 on is correct. The entire state must be taken together. Okay. This does not mean that D1 on and D2 on are correct. It could turn out that D1 on and D2 on are also incorrect. So the entire state must be thrown out. State. So just because one diode is correct, the other one's not correct, the entire state must be redone. So you have to do D1 on, D2 on. And now this time it could turn out that D1 on is incorrect, and D2 on is correct. It's possible, depending on the circuit configuration. So then you have to test a third hypothesis. Okay. And you can quickly see the more number of diodes you have, the more unwieldy the analysis becomes. If you have 3 diodes in a circuit, there's 8 possible states. 4 diodes, 16 possible states. Okay. In this class, I'm not going to give you 16 possible states, 4 diode circuits, maybe 3. Okay, so let's look at an example ideal diode. Okay, so we have 2 diodes in the circuit, D1 and D2. And then we have a voltage source on either side, 10 volts and 3 volts. Okay, so we can identify the number of states. N is equal to 2. Total states is equal to 4. You can quickly write out D1 on, D2 off. Let's do it this way. D1, D2. Can do on, off, off, on, off, and off. Okay, 4 possible states. Looking at the circuit diagram logically, just look at this circuit diagram A. What do you think is the most logical assumption based on the values of the voltage sources and the circuit layout? So we would think this on off. We have 10 volts applied to the anode of this diode. We have 3 volts being applied to the anode of this diode. If we solely look at the anodes of the diodes, we would say the anode is at a higher level than the cathode. Perhaps both of them could be on. But then we see that 10 volts is slightly, I mean, not slightly, it's 10 volts is more than 3 times higher than 3 volts. So there's a possibility that the cathode right here is above 3 volts. So there's a possibility that this node right here is more than 3 volts. If that is more than 3 volts, then diode D2 should be off. Is everyone following what I'm saying? Right? And so the first state I would choose is that D1 is on and D2 is off. Okay? D1 on, D2 off. That's the most likely one. But for explanation purposes, let's choose a state which I know to be incorrect. Okay? So circuit B, circuit shown in B is this state, D1 off and D2 on. So if D1 is off, replace it with an open circuit, D2 on, replace it with a short circuit. Okay, so the circuit has now changed. Circuit has now changed. I'm assuming D1 off and D2 on. This becomes an open circuit, this becomes a short circuit. Circuit has now changed. So I need to prove that VD1 is negative. Remember, diode voltage is always measured with positive at anode and negative at cathode. So I need to prove VD1 is negative, and I need to prove ID2 is greater than greater than 0, positive number. You all with me so far? Okay. So if I was to analyze this, I can quickly find ID2 from Ohm's law. Voltage 3 volts is applied across 6 kilo ohm. So ID2 is simply 3 divided by 6,000, so 0.5 milliamps. So D2 is indeed on because ID, the diode current, is positive. ID2 is greater than 0. So it verifies our assumption that diode D2 is on. Okay. Now we need to find VD1. So here, speaker, that 4 kilo ohm resistor is open. What is the voltage at that end? So this is the analysis for D1. What is the voltage at the anode of D1? It's 10 volts. Anyone else? Why is it 10 volts? No current flowing through. That means voltage is 0. So voltage drop is 0. If voltage drop is 0 and you have 10 volts at one end, that means you have 10 volts at the other end. That's the fundamental concept. So voltage at the anode of D1 is 10 volts. What is the voltage at the cathode of D1? Anyone? 3 volts. So what is the voltage difference? 7 volts with the polarity of VD1 is equal to 7 volts plus 7 volts. So that's our analysis result, that the diode voltage is 7 volts. If the diode voltage is plus 7 volts, the diode should be on. That means our assumption is incorrect. Okay, assumption is incorrect. Now let's take a pause. Let me know if you have any questions. Did the steps make sense? The homework was posted yesterday. That's based on the ideal diode analysis. Okay. So now let's change our assumption, right? Earlier I said that D1 could be on and D2 could be off, and that is what is shown here in C. So if the diode D1 is on, then ID1 must be positive. If diode D2 is off, then VD2 must be negative. The same analysis technique. I would have D1 on, D2 off. I can find out ID1 as 10 divided by 10,000. So 1 milliamp. And then voltage VD2 would be voltage at the anode, VD anode minus VD cathode. And that would turn out to be 3 minus, well, actually 3 minus, let's see, 6 times 1, 6 volts. So minus 3 volts. VD2 turns out to be negative. Hence, our assumption is correct. All right, let's take a pause. Will you write it down, think over it? Let me know if you have any questions. So what happens is the question being asked is, should the 4,000, I mean, should the 10,000 be just 4,000? The answer is no, because this forms a series circuit. Because of D2 being off, all of the current is going through there. So 4K and 6K resistors are now in series. And so the current that's flowing through the diode D1 is the only current that's flowing through both those resistors and the power supply. And so it becomes 1 divided by 10,000. And then the voltage drop across the 6 kilo ohm resistor would simply be 6 volts, 6 times 1. And the voltage drop across 4 ohm resistor would be 4. So 4 volts and 6 volts. You apply KVL, sums up to 10 volts. Okay, so it's 6 volts here with reference ground, and it's 3 volts here. And so VD2 turns out to be negative, minus 3 volts. That's a good question. So anytime you make an assumption about the state of a diode or any device for that matter, whether it's on, off, and you replace it with a short circuit or an open circuit, the circuit changes. Now, how it changes, that depends on the circuit configuration. But every time a circuit changes, you need to observe it again as if it's a completely new circuit, right? First assumption, we have a different circuit. Second assumption, again, a completely different circuit. So every assumption we make, the circuit is going to change, either minor or major change. Okay. So do the steps make sense? Always make an assumption first, analyze, and then verify your assumptions. If it's on, the current must be positive. If it's off, the voltage must be negative. Those are the two primary criteria for each state. Okay. Okay. And let's get small signal models. This is known as the load line analysis. Okay. So this circuit is basically representing a Thevenin equivalent circuit of a large linear network. So you have a voltage source and a series resistance that is being applied to a diode. Does not mean that it is simply one voltage source and one resistance. This could be like a Thevenin equivalent. Okay, Thevenin equivalent. So you have a voltage source, you have a resistance in series, and you're applying and you're connecting a diode to that circuit. So it's a series circuit The current that is flowing through the diode is the same that's flowing through the voltage source, is the same that's flowing through the resistance. Okay, it's a series circuit, so everything's all the current is the same, which is similar to what we did in lab 3. Okay, so that's the simplest diode biasing circuit. Now, analyzing a diode, meaning it means to determine the diode voltage and the diode current, ID. Okay, there is a specific term for that, and that is known as the Q point. Anyone hear of this before? So it stands for quiescent. Quiescent. I hope I spelled it correctly. Quiescent in the English language means it's lying dormant. In this case, when it's applied to electric circuits, we are saying that we have applied a DC voltage to our circuit. Now the circuit is lying in a dormant, or it's not quite dormant, but it's lying in a prepared state to accept AC input. This is especially important when we get to BJTs, which is like next class and then next lab next week. Bipolar junction transistors, diodes, we're applying DC voltages, and we set the diode or the transistor to operate at a fixed point. DC is constant, doesn't change. So it's operating at a fixed point. That point is known as the Q point. So every Q point is described with voltage and current. Some authors like to use current and voltage, just change the order of things. Y-axis and x-axis. VI or IV, doesn't really matter. But the Q point is basically fixed. Okay, the Q point is fixed. So we are fixing the Q point by applying a DC voltage. That's what we did in circuit number 1 of lab 3. We determined, why is this not working? We determined the biasing points of the diode, right? We set the voltage, input voltage, and depending on the input voltage, the diode voltage and the diode current changes. As long as the input voltage is the same, diode voltage and diode current remains the same. So the circuit is now lying in wait, or it's prepared to accept AC input. Now, when we apply AC input on top of the DC biasing, obviously depending on the electronic device that you're using, the output would change. For a diode, if you have a characteristic like this, right, diode characteristic, I'm going to enlarge this here. Let's say diode characteristic is like this. And it climbs, becomes kind of linear. Okay. If you apply a certain voltage, you're going to get a Q point, right? Now, if you apply a small AC voltage on top of this Q point, top of the DC, your Q point is going to move up and down the diode characteristic curve. Okay. So this is an applied AC signal. And it's typically small in value. It's going to shift that Q point either up or down, depending on the voltage that you're applying as the AC input. So when it moves up and down, your Q point is shifting in response to the AC input. Okay, it's changing in response to the AC input. If you take, well, actually, let's talk about slope in the next slide. But the Q point shifts up and down, right? So if we want to determine the performance of our circuit, meaning the response to the AC signal, we need to first establish the Q point. So there is a graphical technique to determine that Q point. Okay. So we have the diode equation, right? The diode equation has ID and VD. Those are the two unknowns. Now, if you have two variables, how many equations do we need to solve them? Two equations. We have one equation that's a diode equation that's already plotted here, given to us. Then we need to plot a second equation, and we're going to plot this as a linear line. And that line is known as the load line. Okay, hence load line analysis. Okay, load line analysis is a very handy tool. We can use that for diodes, Zener diodes, transistors, amplifiers. It's a graphical analysis where we can solve equations graphically. Okay, so since we have two variables, we need two equations, we need two graphs or two plots. We have one plot from the diode characteristic, and then this is the load line. Okay, and the way we find the load line is apply KVL around the circuit and generate an equation. And we can write Vs is equal to ID times Rs plus Vd. One source voltage divided across the resistor and the diode. Right? So Vs is equal to ID times Rs plus Vd. Now, two unknowns, but if you can plot this as a straight line, again, because it's at one single point, just at the Q point. So we can treat it as linear at that point. Okay. So to plot this, we take the two endpoints where it intersects the X and the Y axis. Choose values ID equal to 0 and VD equal to 0 and solve for the other quantity. Okay. If ID is equal to 0, then VD is equal to Vs. That's one endpoint. And if VD is equal to 0, then ID has a value of Vs over Rs. And so these two endpoints gives us the load line for this circuit. And so you see when ID is 0, diode voltage is Vs. And when diode voltage is 0, the current is Vs over Rs. Once you have those 2 points, we can join them, get our line or load line. And the intersection point of the load line and the diode characteristic gives us the solution to our circuit. You extend the points to intersect the X and Y axis. That gives you the operating point or the Q point for the diode voltage, VQ and IQ. Those are the operating points. So it's already 2 o'clock. If you need to leave, you can leave. I'm just going to continue recording for a little bit more. Does the load line make sense? Right? That's the load line analysis. So typical load line analysis always begins with applying KVL to generate an equation. That equation will have two unknowns, a voltage and a current. Since there are two unknowns, we find two endpoints by choosing both values as 0 and solving for the other one in two separate steps. So we first solved by choosing ID is equal to 0. We found VD. And when we choose VD is equal to 0, we find ID. Find those 2 points, join them together. The intersection points with the diode characteristic is the Q point or the solution for our circuit. Okay, that's the load line analysis. Now, the load line analysis is not always very helpful. It's a quick and I wouldn't say quick and easy, but it's one of the tools at our disposal that we can use for analyzing a circuit. But because it relies on a graph. Nowadays, of course, we have digital, sources and software that we can use for graphs, so we can get precise values. But previously, when it was hand drawn, it was not always, it would not always provide a good value because it's limited by the size of the graph and the accuracy of the engineer. So we want to find how and where the Q point would shift, right? There's something known as piecewise linear model. Okay. In the piecewise linear model, we model the diode on diode as a series resistance in this portion of the diode characteristic. So current rises exponentially after it turns on, and then we can consider that this portion after it turns on to be linear. So we take a piece of the diode characteristic and we make it small enough that it's linear, and we can apply linear analysis techniques to that section. Hence the name, piecewise linear analysis. Okay, piecewise linear analysis. This is the technique that is used in physics, electric circuits, many other operations, many other systems. So in this, we are going to plot the diode characteristic as a linear line, extrapolate it to the x-axis, and we're going to say, when we extrapolate it, this represents the diode turn on voltage. Okay, diode turn on voltage. Here it uses V gamma, and gamma is not a capacitor, it should be a voltage source. Anode is plus, cathode is minus. Okay, that simply shows a little bit of voltage that is turning on the diode. So when you have your Q point and you have the diode characteristics, you take it and represent it as the linear portion. If you measure the resistance at the Q point, you obtain what is known as a static resistance. Static resistance. So diode has static resistance and dynamic resistance. Dynamic resistance is something, static resistance is something you obtain in the biasing circuit, because we're only looking at one point. If it's one point, it's the resistance only at that operating point, hence static resistance. Dynamic resistance is used when you apply an AC signal on top of your DC. So your Q point is shifting up or down the characteristic. And when it shifts up or down, we take 2 points on either side of our Q point, and we model the change in voltage versus the change in current. And we get, what we obtain is the dynamic resistance. So we use RD for both. In the lab, we performed the experiment lab 2, circuit number 1, where we extracted RD parameters. That is the static resistance, because it's only at one point. If it's between 2 points, then it's dynamic resistance. So in this case, if you take 2 points, again, you can take any 2 points, and it gives you the diode resistance between those 2 points. So in this case, because the line is linear, it simply is the change RD, diode resistance, is delta V or delta I. And because it's a linear line, if you're extracting information from the line itself, we can say it's the slope of the line, which is 1 over RD. Okay, slope of the line, 1 over RD. So that becomes delta I or delta V. Okay. So we'll end class here today. We'll pick up here again on next Monday. On Friday, I want to cover a little bit of the BJT in the bipolar junction transistor. So that will prepare students for the amplifier circuits that will perform in lab 3. Okay. So I'm going to skip over a few things in the diode, and then we'll come back later just to synchronize the lab with the lecture. Yes. No. Well, actually, yes. So thank you for reminding me. I was working on it earlier today, but I haven't yet finalized it. So I will post a notice once we are done with today. So maybe late today evening or later tonight. I'll post it. Yes, anytime on Friday. And then it's also, I think, settings will allow me to set it like a slight penalty on Saturday. So let's see. All right. The report stop. How do I stop this? Stop. How do I stop?
There you go. This way. Yeah.
Is anybody even in the meeting?
No, nobody's in the meeting right now. Yeah, it's just recording.